Hello and welcome to our session, Quantum Computing in Alteryx, the Future of Logistics. Since the early 1980s, the idea of quantum computing has captivated the minds of physicists as well as those outside the scientific community. Due to its potential to deliver exponential speed increases over classical computing and the possibility of delivering solutions to highly complex use cases, the desire to apply quantum computing to real-world problems is stronger than ever. At Aimpoint Digital, we are passionate about staying on the leading edge of artificial intelligence and machine learning innovations. With quantum computers finally operational, that vision is more important and relevant than ever. As part of our mission to drive powerful analytics into the hands of everyone, we have brought together the ease of Alteryx with the complex science of quantum computing by integrating IBM's quantum computing service, IBMQ, with Alteryx. In this talk, we will give a brief background of quantum computing, demonstrate a live-run quantum algorithm within Alteryx using Aimpoint Digital's Alteryx quantum extension, and discuss potential applications to drive value in current and future business contexts. My name is Jamie Laird, and I am Principal Consultant at Aimpoint Digital. I have been an Alteryx user since 2015 and hold 8 certifications in Alteryx, including Alteryx Expert. I'm also an active member of the Alteryx community. I will be guiding you through today's session and will be delivering our basic introduction to quantum computing. Our second presenter, Philip Mannering, is Senior Analytics Consultant at Aimpoint Digital. Philip is a certified expert in Alteryx, US Alteryx Grand Prix winner 2019, and Alteryx Ace, and has a Master's in Theoretical Physics from Durham University. Philip will be delivering our demo of the Alteryx quantum tools today. Aaron McClendon is Head of Data Science at Aimpoint Digital. Aaron led the development of the Alteryx quantum tools. At Aimpoint, he has developed advanced solutions for industry, as well as authoring academic research. Aaron specializes in advanced machine learning, demand forecasting, and time series analysis, and has master's degrees from the University of Stuttgart and Max Planck Society. All computing systems rely on the fundamental ability to store and manipulate information. In classical non-quantum computers, this information is represented by what are known as bits. A single bit represents a logical state with one of two possible values, 0 or 1. The encoding of data by discrete bits was used in the punch card systems found in early computers developed by companies such as IBM. In modern computers, a bit is usually represented by an electrical voltage or current pulse. Computers need a way to manipulate these ones and zeros in order to carry out complicated calculations. To do this, they use logic gates. Logic gates transform ones and zeros, accepting an input and then outputting a result based on their state. The simplest classical logic gate is the NOT gate. A NOT gate accepts a single input of either 1 or 0 and outputs the opposite value. If the input is 0, the output is 1. If the input is 1, the output is 0. By combining many of these small and simple operations, we can build highly sophisticated computer programs. Quantum computers leverage the unique and somewhat counterintuitive properties of quantum mechanics to manipulate information. Quantum mechanics describes the behavior of matter at the subatomic level. At this scale, matter doesn't follow the same rules as objects that we can see, feel, and hold. Because they are governed by the laws of quantum mechanics, quantum computers work very differently to classical computers. The fundamental unit of information in a quantum computer is the quantum bit, or qubit. Unlike the bits used by classical computers, which can be either 1 or 0, qubits can be 1, 0, or a linear combination of both at the same time. The ability for qubits to exist in multiple states simultaneously is known as superposition. Superposition refers to a combination of states we would ordinarily describe independently. Whereas a classical bit can have the state of either 1 or 0, a quantum bit, when in the state of superposition, has both states at the same time. Because qubits are so different to classical bits, we cannot use conventional logic gates to manipulate them. Instead, quantum computers use what are known as quantum logic gates. Quantum logic gates are the building blocks for processing information in a quantum computer. Unlike classical logic gates, quantum logic gates have the ability to process multiple possibilities simultaneously. One example of a logic gate is the Hadamard gate, which takes a qubit into superposition. Superposition, entanglement, and another quantum effect called interference are what makes it possible for quantum computers to perform multiple calculations, considering multiple configurations at the same time. But what does all of this have to do with logistics? The key point to take away as we think about applying quantum computing to the challenges of logistics is that because qubits can exist in multiple states at once, quantum computers have the ability to evaluate many possible outcomes simultaneously. A helpful analogy is to think of a quantum computer as being able to look down every path of a maze at once to find the way out. Anywhere there are large, uncertain, and complicated systems that need to be simulated, quantum computers will find a use. Quantum computing holds the potential to revolutionize the future of logistics. Scheduling, planning, routing, and traffic simulations are all examples of highly complex real-world scenarios where the ability to evaluate large numbers of possible scenarios simultaneously has clear relevance. Forecasts and simulations are a common and crucial element of the modern logistics industry. But the sheer complexity of the systems and the difficulty of accounting for every possible permutation when running simulations mean even the most powerful classical computer will struggle to keep up with the demand for real-time, actionable information. Quantum computers, on the other hand, are extremely well suited to addressing these types of highly complex scenarios. Returning to my previous analogy, this ability for quantum computers to look down every path of the maze at once can transform the way in which simulations are carried out. Imagine a company plans to ship orders over 3 possible routes using 10 trucks. This means the company has 310 possibilities, or 59,049 solutions, to choose from. A simple task for any classical computer. Now imagine that instead of 10 trucks, we want to simulate 40 trucks over the same 3 routes. In this case, the possibilities are approximately 12 quintillion, an impractically large ask for even the most powerful of today's computers. Quantum computers, on the other hand, are well suited for problems like this, where we need to test many combinations. There are a growing number of examples of logistic companies using quantum computing to do just this. In Japan, Coca-Cola Bottlers is using quantum computing to optimize the company's thousands of daily supply deliveries, while in China, Volkswagen has developed quantum computing algorithms to optimize taxi routes in Beijing. Although quantum computers are still rare and expensive to operate, in recent years, companies such as IBM have made their quantum computers publicly available via APIs. As Philip will show you in the following demo of Alteryx Quantum, we can leverage these APIs to bring quantum computing into the simple and familiar environment of Alteryx.
Hey folks! Alright, now it's time to dive into Alteryx. So before I get onto the quantum stuff up here, I'm going to first show you a classical analog, and I think this sets the framework for how we're going to approach the quantum problem in Alteryx. So in Alteryx we can create a bunch of gates, ANDs, ORs, NANDs and NOTs, and using a complex system of gates I'm going to show you that you can actually add 2 4-bit numbers together. And I find this quite astounding that just by putting ands and ors in the right order, you can take two numbers, let's say 13 here. I'm going to run this so I can show the output. 13 in binary, and if I input 1, we get this in binary. And just by using AND and OR gates, we get the output over here in binary, and then I can read out that number over here, and we get 14. So just by elementary gates, logical gates, we can add two numbers together. And just to show you what this looks like, we can package this container up into its own macro, this adder macro here. And if I scroll down, I can show you what that looks like. And again, 5 in decimal looks like this in binary. And let's add, say, 5 again is boring, let's say 13. And if we run that, then 5 plus 13, you can see every time we add a 1 and a 1, we need that carry to go to a more significant bit. So it goes from least significant bits, cascades down to more significant bits, and then we get our result here, 18. So that's just a look at how classical gates, how we build that into Alteryx. And you might say, well, you've cheated here, you've used more kind of exotic type gates here. You've got the XOR and the NAND, but actually the XOR gate in true macro inception fashion is composed of yet more gates. So the XOR gate is the OR gate, and the NAND gate, and an AND gate. And the NAND gate itself, again, is a combination of AND and NOT. And if you want to see what the AND looks like at its base, we're just doing a formula tool. We're just doing a binary AND in there. That's what's going on. So with that in mind, now let's start to look at the quantum side of things. Now things start to get a little bit interesting. Instead of dealing with bits, we have qubits. So let's start to build our quantum circuitry. So I have this quantum tool palette here, and you can see a variety of gates, which we're going to expand upon, but a variety of gates to manipulate our qubits and create our quantum circuits. So the first thing I want to do, well, the first thing I have to do is add a qubit. And I can decide whether to initiate that qubit in the 0 or 1 state. And then now if I want to manipulate that, I can add a series of gates. But before we do that, let's add a couple of browsers and run it and see what it looks like. So we can't actually see qubits, but we can show a representation of them. So once I've run this, I can see in the browser here, kind of gives us a report and shows us what's happening. So this gives us the circuit diagram so far. And then we have the block sphere, which is kind of a graphical representation of the probability that we'll find it in either state. So we can see that because we initiated it in the 0 state, that arrow is pointing towards the 0 ket vector. And then if we were to measure this, it will give us state probability. So we haven't measured this yet, but it's we can run it in a simulator and we can get the state probabilities. And this is saying that it's 100% likely to be in the 0 state. Okay, so now let's add some more gates and see what we can do with this. All right, now let's add an XGate. And this will perform a pi rotation about the x-axis of the block sphere. So it essentially flips the 0 state to the 1 state. So let's have a look at that. Reconnect this browse to the report anchor and run it. And now we see that from the report the circuit diagram has updated. So we've added this XGate and it has indeed flipped the state vector, and furthermore, if we were to measure it now, we'd have a 100% chance of having it in the 1 state. So this isn't terribly interesting, but what is interesting, or what starts to become interesting with qubits, is that we can put it in a superposition of states by using the Hadamard gate. And the description here is a fundamental gate moves away from the poles of the block sphere and creates a superposition of 0 and 1. So I'll add that again to the output and add a couple of browsers to it. And now run. Now we see that we have our circuit diagram again updated, and we are now on the equator of the block sphere. So now it's 50% in the 0 state and 50% in the 1 state, and we can see this again in this histogram down here. And so finally, for this example, we might want to now measure the output, and this has quite an important property. So if we were to add the measure tool, the report anchor again, so we can see what's going on. Now, whenever we make the measurement, it will, so to speak, collapse the wave function. So the very act of measuring it means it has to choose a state, and that state will be random, especially now because it's in the superposition of 0 and 1, then it has to make up its mind and choose either 0 or 1. And so the circuit diagram now shows we've measured it, and the block sphere doesn't really make any sense after you've measured it, because it doesn't, you know what the probabilities are, because we know for a fact it's had to choose a state. So this is the block sphere before measurement, and we see that whereas before it was the superposition, 50% likely to be an either state, upon measuring it, it has to choose a state, and in this case it's chosen the 0 state, but that's completely arbitrary. It could have chosen the 1 state with equal probability in this case. Okay, now let's build a circuit that can create or simulate random numbers. So I'm going to add a bunch of qubits, and I'll keep them in the 0 state. And now to move them into the superposition, I'll add Hadamard gates to the outputs. And to combine these all together, I'm going to just use the union tool. I'm going to use a little trick to connect all these together. If I view possible connections, and then I want to connect the input union and output from all the output Hadamard anchors, and this one too. Yeah, looks good. So if I connect all those tools up, and now finish by using an executor tool, which is kind of like a measure tool. It does measuring, but it gives us the option to run multiple times, and it will also allow us to select what backend we want. So up until now, we've just been using the Chasm simulator, so a simulator, but we can actually run this on quantum hardware, and I've got my API token in the tool, so it will run on an actual IBM quantum computer, which is pretty cool, I think. So let's start just by using a simulator, and then we'll try the quantum hardware later. But if I select simulator and run, and now if we look at the report, we can see that it's showing us the complete circuit diagram, and now it's outputted to actually 5 classical bits. So whenever we read out a result from a quantum computer, it will always be in the classical bit. So these get read out. We can see the states before. These are all in the superposition states before we measure, and this is our output. Now it might look like something funny's going on here, where this is a lot more likely than the others, but we only did run it 15 times, so there's a if we measured it 1,000 times, then this would flatten out with the law of averages. But now I'm going to show you what it would look like if we ran it with quantum hardware. Now this is really cool, and it sends it to an IBM quantum computer, but it does take a while to run, because it gets queued and it takes a while. So I'm going to set this to 1024, and I'm going to run this. All right, so having ran that now on a real quantum computer, we can see the results here, and you can see it's a lot more uniform the distribution. And we also get out the binary number, the decimal, and the number of counts for that outcome, for that quantum state. And it's these amplitudes here, the probabilities, the count, when we run it multiple times, that will allow us to run more complicated algorithms, and then building the circuitry in Alteryx, come up with some answers. So, thank you for watching. At least he's alive, I suppose. That's a Schrodinger's cat reference for you.
Thanks, Philip. We truly believe that quantum computing has the potential to revolutionize the future of logistics. We also believe that in order to reach their full potential, advanced technologies such as quantum computing must be made accessible to the everyday analytics user. That's why we're so excited to have brought together the simplicity of Alteryx with the transformational power of quantum computing through our Alteryx Quantum package. We plan to make Alteryx Quantum publicly available through the Alteryx Gallery later in 2021. If you'd like to find out more about Alteryx Quantum, myself, Philip, Aaron, and the rest of the Aimpoint team would love to talk to you. Please reach out to us via quantum@aimpointdigital.com. Thank you for attending this session, and we hope to talk to you soon.